63. We're still in chapter 1, section 1.1, and we're working problems. And this is problem number 17. And again, I'm going to go through the setup, but I won't actually solve it for you. Consider a rod being cut to a length, and the length can never be perfect, so it must be cut for never perfect, and so must be cut for accuracy based on a desired tolerance. Tolerance is the amount that a measure can vary above or below a design size. Let me explain what that is. Let's say that you're hired to do something. You're hired to deliver. I make tables, and I need legs, and you make the legs. And I need the legs to be a specific length. I need them to be, I don't know, 30. Let's say I need for it to be 34 and 5/8 inches long for some reason. And you say to me, yeah, I can do that. I can deliver all you want. But, you know, might not be exactly 34 and 5/8. Maybe I might vary by a quarter of an inch or something. And then I'm going to have to decide whether that's acceptable or not. Okay, so that's tolerance. That means that you could go greater than this. It could be longer than this by a quarter of an inch, or it could be shorter than this by a quarter of an inch. I mean, actually, a quarter of an inch is an awful lot. Can you imagine a table where 2 of the legs are one thing and 2 the other? Not a good idea. Okay, so anyway, in this particular problem, what I want is referred to as the design length. That's how I'm designing my table. And these are the values. And, you know, I notice I have a couple decimals here, and there's a fraction involved here. Got inches, centimeters, inches again, and metric meters in this case. The tolerance for this guy is that he can vary by 0.034 inches. This guy can vary by 0.15, this guy by 1/32, and so on. I want you to notice something on here. The units are different, okay? I have meters here, but I have centimeters over here. We'll talk about that in a second. So if I want to know what the maximum length is, all I really need to do is take that design length, and add the tolerance to get the maximum, okay? And if I want the minimum, just take that design length and subtract the tolerance, and that's what's going in there. So when you are doing this and submitting your work, even though it's not very much, make sure that you show the setup that you're using in order to answer the question. Okay, so let's talk about this metric business over here. If this was centimeters, it'd be a slam dunk. You know, just take the value and you're going to either add 0.06 or subtract 0.06. But this is meters, and you're going to have to change this over to centimeters. And how do I know that? Because they have centimeters already set up in here. So you need to know 3.2 meters is equal to how many centimeters. And this is where your appendix comes in. And if you were to look on the very first page, the relationship between meters and centimeters is right here, meters and centimeters, in the length portion of your table here. 1 meter equals 100 centimeters. And most of us are going to remember that. Some of us might not. 1 meter equals 100 centimeters. That's what I have right here. And later on, you're going to learn how to do conversion chains very specifically. And so I'm just going to show that to you right here. If I want to change 3.2 meters over to centimeters, I can do this little mini chain. It's kind of a slick process. And I'm going to take this information and I'm going to plug it in here. And how do I know which one goes in there? Was the 1 meter on top or 1 meter on the bottom? Well, here's how you know. If the meters are on the top on this part, they have to be on the bottom in this one. So 1 meter goes on the bottom and 100 centimeters goes on the top. And then it's just an arithmetic problem. So if you take 3.2 and you multiply it by 100, but the zeros, you're just going to swing that over a couple places. So it's 320 centimeters. So before you do this part of the problem, you're going to have to use that conversion. And number 18, we're basically talking about the same thing. Calculate the difference, a little bit difference. Calculate the difference between the design size and the actual size in the chart. Here's the design size. Here's the actual size. And we want to know what the difference is. Now, well, you know, it's just subtraction. That makes sense. But note this, this comment over here. Actual sizes that are less than the design size should be denoted with a negative number. So if your actual size is less than this, that means you shorted it. right? You made it too small. So you're off by a negative. If this guy was greater than him, and he is, then your difference is going to be positive. Okay, and that's the difference between these two. This guy over here is less than him, so that guy should be negative. And the last thing that's on here on number 19, I'm really not going to discuss this with you, probably not at all, because I am going to assign this as an application activity. Um, and I'll be giving you more information about that later. We're going to be skipping problem number 20. It's not going to be an application problem nor a homework problem, and I'll make sure that that's noted on your schedule. Let's take a look at number 21. We've got a couple more to go. Consider the diagram, this guy over here, and convert the dimensions to fractions to the nearest 1/100th of an inch. Don't simplify. Use a tolerance of that much, plus and minus 2 over 100, and determine the maximum and the minimum allowable dimensions. So let's look at this. So they have this length right here, 80.5, and that little width there is 3.7 inches. This guy is 100.29 long at 36.62 high. Okay, so let's take a look at the table and make sure everything is abundantly clear. These are the design lengths, 1, 2, 3, 4. So there's 4 rows here. But notice that the tolerance is given in terms of a fraction. So what you want to do before you get going on this is to go ahead and convert this guy over to a fraction, and you might have to modify it. So please pay close attention to the explanation. If I say this correctly, this is 3 7/10. And if we were on the phone and we said that, I wouldn't know whether you meant that or whether you meant that, because they're both said the same way. But because I want to take care of this tolerance, I want to add it for the high and subtract it for the low. I want this to be in terms of hundredths also. And it's really easy to change it. Add a 0 here and add a 0 here. So what's going to go in this spot right here is that number. And then you're going to show that it's being added by that amount for the maximum and subtracted by that amount for the minimum. On this guy, if you say him correctly, he is 16 and 62 over 100. And that's the number that's going to go in this box first, and then you're going to do the same thing, adding and subtracting. So it's just a very simple math thing, but make sure that you do that conversion first. And finally, on number 22, we've got one more where we're doing maximum and minimum. It says consider the diagram. It's got all kinds of information in this diagram. There's an end view and a side view. This is an isometric view, which means that it's kind of on an angle, and you'll be learning about isometric views when we have the measurement section, which is in chapter 2. Okay, consider this diagram and determine the maximum and minimum allowable dimensions. Same thing that we did before for the given tolerances in the table below. Answers should be simplified. And just as a matter of notation, when you see that sort of thing, it means that they're talking about a diameter. So in this diagram right here, there's a little symbol. It's kind of hard to see, but it looks like this. And then it says 8 5/16. This means that that number is the diameter of that as opposed to the radius. If it was the radius, it'd probably show an R like we have in the past. Okay, so what we want to do here is just take these guys. Here's the design. You want to add an eighth in order to get the maximum, subtract an eighth in order to get the minimum. They should be pretty straightforward. You're probably going to be doing these in your calculator anyway. Just show me that you're adding and subtracting and show me your answer. That's what I would be expecting to see. So that's the last problem in this section, and we'll be moving on to section 1.2.